Hi everyone, welcome to this chance of my presentation on this conference. And the title of my today is Scalable Structure of Correlation Control with Edge Computing for Large-Scale Smart Farm. I'm Hee-Dong Park, working with Jungbu University. At this particular time of this year, this social distance method of getting information and presentation is ready. And thank you for this technology. And the technology is wonderful. Let me start by talking a little bit about why there are huge challenges in great balancing of global social and industrial status. It may be classified into three categories. The first is to close food gap between countries or economic classes. It requires increasing in food or harvest to feed billions of people in the world, especially to food shortage countries. And the second is supporting economic development for all countries, because a significant number of global population will be directly or indirectly employed by agriculture. The last is reducing environmental impact, such as reducing carbon dioxide emissions, and also from farming. So does global gas emission from agriculture greenhouse and land use change. Maybe one of the efforts can solve or support these challenges is a smart farm technology, I think. Now, I think almost people recognize the smart farm concept. Smart farm system refers to a farm that can manage the growing environment of crops in a greenhouse, and even livestock remotely and automatically using the great IT technology. In here, the environment we should concern for greenhouse can be measured as values of parameters such as temperature, humidity, carbon dioxide, soil status, and etc. And smart farm can also control the greenhouse environment using many kinds of actuators or equipment, such as for nutrient supply, ventilation fans, coolers, heaters, and electric motors per side or ceiling position. Until now, the important function of smart farm is the automatic control service based on real-time farm field data and control many devices upon these collected data. However, there are increasing needs for getting high performance and more complex functions as the farm becomes bigger and complicated. Let's think about data. The collected greenhouse data itself may not be important. Sorry. But collected or stored data analysis is very important part of smart farm operation. And now, powerful analysis for getting predictive algorithm and even machine learning is required. These advanced and intelligent tasks were handled by cloud server now for current smart farm management or control. However, think about when the network or cloud server is not connected or failed. In other words, when a failure occurs, the need for minimum farm automation function also need to be carried out. That's why we discussed the need for edge computing in advanced smart farm environment. As mentioned before, current cloud-centric smart farm architecture is a good solution, but has some problems to consider for advanced operations of smart farm system. The first is security issues while using a network, the internet, an open system. The other is network congestion because of enormous data collection from many farms to transmit to cloud. And the last is cloud computing cost because the number of connected smart farm increases year after year rapidly. As an example, in CCTV, most operating time is spent on standby. So most of the data may not be meaningful video data. So it requires the technology to analyze the video data more accurately and send only the filtered data for motion detection or sudden intrusion from outside to the cloud. Now, I will propose a scalable architecture of correlation control level using edge computing for smart farm system. This is based on two-stage control system for efficient and intelligent management, and using edge computing concept with possible lightweight big data and edge artificial intelligence technology. In general, the flow of smart farm control can be divided into devices, local control layer, and network and cloud. Okay. The device layer where sensors and actuators are connected, and a local controller to collect data and drive the actuators, and network the internet for data transmission. And the last is cloud layer for data storage and analysis. This flow is good, but as mentioned before, when the network or cloud server is not connected, the minimum farm automation function needs to to be carried out. Moreover, it requires its own farm management, not only standalone operation, but also advanced operation cooperation with cloud server when connected. Our cloud edge computing based architecture, as shown on the right side in this figure, supports this operation. And in addition, the scalability by interconnecting other smart greenhouses with correlation control structure level. Most smart farm can be operated in a Bayesian method with automated and remote controlled devices based on the analysis of data from the sensors for optimal greenhouse environment. This conventional smart farm control includes conditional analysis level, which is one of our two-stage control structure. This table shows some parameters items associated with greenhouse according to our two-stage control level. The parameter items may be light, environment, air conditioning, ventilation, watering, nutrient supplement, and etc. In conditional analysis level, it simply make automation based on the sensors data. However, in correlation control level, it has an intelligent structure, and it provides correlated results of advanced processing. We know that it's necessary to extract optimal value by making a prediction model with farm environment, and data analysis from various external and internal parameters can be executed. So the predicted results are calculated and finally applied to the smart farm system. This figure shows some parameters for data analysis and prediction from sensors and conditions of greenhouse as a model by correlation. Therefore, it needs to synthesize the data inside and the statistical data collected so far related to a specific crop, and also execute to make result by local processing appropriate to the weather and environment. Some parameters are affecting each other, and sometimes with feedback characteristics. We previously, maybe last year, proposed a two-level architecture for greenhouse to provide an automatic system focusing on the lower conditional analysis control level without upper correlation level. In here, we are going to focus on the upper correlated control level. This level will make results using conditional control level with respect to the other local or external intelligent data. It can also make training and prediction data, for example, with geographical regional dependency, harvest time, and etc. So, utilize edge computing or lightweight big data and built-in edge artificial intelligence if possible. This structure shows functional blocks at each two control level. We can see from this figure, it performs more intelligent and complex processing at the correlation level than the conditional level. Okay. Very complicated. From the proposed two-stage control architecture, as we can see in this figure, the upper correlated control level can be connected to the other correlated interface by connecting IoT gateway or complex control device. It has local storage to collect and store all data from farm, but only send the extracted data or feature to the upper stage, and can be related to data analysis with monitoring and training, and prediction control as a model as shown before. Okay, next. Again, the upper correlation level processes the data from the lower conditional control level and send the extracted features or data to the upper stage, the cloud. It can support a lot of functions in cooperation with the cloud, such as adaptive light control by crop type, adaptive indoor environment control according to the external conditions with energy-saving functions, cooperating prevention for pests or diseases. While cloud server supports conventional smartphone processing functions. Here shows the diagram in correlated or edge computer control processing. In correlation control level, modeling is performed by analyzing the inputs. The input was stored in the previous training process, and also with the internal data actually collected, and then run the algorithm if possible. The results will be stored in the internal storage or database, and this can be used as input for future intelligent control. The data selected and processed in the correlation control level will be transmitted to the cloud server, and the server executed a function such as additional processing, deep learning, and prediction to return the final result. Since the cloud server collects pre-processed data from the edge computer, It processes small capacity data than the original of the edge computer, so reducing the congestion of the entire network and the processing burden on the server. In the correlation prediction control stage, it executes smart pump control while going down to the conditional control level based on the input of previously stored parameters and control values from the cloud server. Since edge computers have low performance compared to the cloud server, so lightweight technology such as parameter removal, sharing, or model compression, knowledge distillation, and acceleration can be applied to the edge computer. Smart pump technology is becoming more intelligent, such as prevention of pest, harvesting, and now even prediction management in advance. So we are now at the point of innovative smart pump system, which includes through the application of big data and artificial intelligence. Therefore, this rapid development has made precision farming possible. Excuse me. And the need for scalable structure and the standardization framework of smart pump. Think about other challenge. Outdoor smart pump. It has more sophisticated parameters to consider, unlike indoor greenhouse control. There are many considerations such as irregular changes in weather, various and sudden natural disasters, control of irrigation and nutrient solution according to the soil status, and adaptive soil management by short-term precipitation or rainfall. So increased efficiency can be made by interworking with edge computer with the architecture presented in this paper. Conclusion. In this paper, we propose a smart pump architecture in the correlation control level, focusing on one of the two-stage control structure with higher level, and this can reduce the burden on the cloud server and enables local control independently in case of cloud or communication failure. So it supports advanced functions, operation of large-scale smart pump through interfacing with cloud servers, and training before delivery to the server. And finally, we hope it can be used as a standardized control framework for smart pumps in the future. Okay, thank you for your listening.